So, I am not drawing the complete gate driver, you can think about this is your driver. So, this is your minus plus ramp. This is your, let us say, PID. Okay. So, this is your single phase buck. Now, what I will do, I will add another inductor, and this will be generated from another comparator with the same V control, plus minus. So, if I call it V ramp 1, this is V ramp 2. So, the way it is done, that Vp Wm2. So, we have two PWMs and the duty cycle will be same. I am thinking about your V control is common and your V ramp has the same amplitude 0 to Vm, this is also 0 to Vm. So, duty cycle should be same, but we keep them out of phase. So, what will be the, so if this is L1 and this is L2, what will be the currents? How the current will look like? So, if this is load, let us say I load, IL1 will be rising or falling during this time? Okay, because this is operating at VPWM, falling, rising, falling. IL2, what would happen? Rising or falling? Then what is the average? What is the average of this? I load by 2. So, if I add the 2, correct, what will happen? So, let us say it is a 50% duty cycle, rising and falling slopes are same, what will be the current? DC? Where is the ripple? Ripple is cancelled out, huh? 0 ripple. This 50% duty cycle, huh? And what will happen at non 50% duty cycle? You will have ripple. Will that be higher or smaller? So, this is D equal to 0.5. Let us take another case, D equal to 0.25. So, okay. this is your half period. And they are 180 out of phase. So this is 1/4 period and this is 3/4. So it should be here. It will be coming exactly at the center, 180 out of phase. It's a half cycle delay between the two. So now IL1 different slope. This guy will be here. So falling or not falling, rising and then falling here. Okay. So if I add the two, what will happen? What will happen? So you have positive ripple and negative ripple, correct? So still you get some cancellation there, and then here both are positive. So which one has a higher slope here? Positive or negative?
Positive.
Huh?
M1
So it will be something like this, Then what will happen here? They will be falling, correct? Both are falling, in this portion. Then next, what is happening? Again you will get positive. Then here. So it will look like a 50% duty cycle, but what is the frequency here? What is the frequency? Twice of
2 times
FSW. And when you increase the frequency, you know what happens? Your ripple will reduce. So your profile will look like this. If I call it delta V out, and this is your D, duty cycle. We know that this was the profile for single phase. If, let me give us some, if this is 1 means it's normalized to some value, okay. If it's 10 millivolt, you can say divide by 10 millivolt. Then 2 phase, we know at 50% what was the 0, and it will peak at and this guy will be half. Now if I add, let's say, one more phase, or let's say 2 phase, 4 phase, just keep it simple. So it will do this will be 0.5, 0.25. So when you have a 4 phase, then you will get a 0 ripple at 0.25 and 0.75, and this will be 1/4. So your ripple is actually 1 by nx, where n is number of, let me use different color, single phase ripple. Okay, n is number of phases, and ripple frequency is n into FSW, and 0 ripple occurs at 1 over d over n. Okay, and d over n plus 0.5 both side, it's a symmetric curve. So 1 over n, 2 over n, so 0.5. So the number of 0 points will be n minus 1. Okay, and your duty cycle at which it will go 0 will be 1 over n and 2 over n until n minus 1 over n. Okay, so this will be n minus 1 over n. So that is the advantage. One is the ripple. Now let us see the losses. Losses in multiphase. By the way, by doing multiphase, what is the disadvantage? Advantage, we know it's a ripple. Can you tell me disadvantage? Just by looking at this. Yeah, it requires more components, more number of inductors, more number of power stages. Okay, even let us say controller is not taking too much area and your control is common, so extra you require PWM modulator only. So extra comparator will not cost you much, but power FET are very large, and inductor is also external component. So it will basically making the cost almost double actually. So yeah, so what you do, you equally split the power FET. So instead of sizing the same, let us say you require 100 milliohm for 1 amp, and now it will be catering only 500 milliamps, so split into half, so that your total area of power FET remains same. But what about inductor? I cannot reduce the size of inductor. Capacitor you can reduce, because now the ripple frequency is 2x. So for the same ripple, you may require half of the cap for 2 phase, or if it is a 4 phase, 1/4 cap. But inductor you cannot do anything. Inductor is carrying the same frequency ripple, same amplitude. The only difference is carrying lesser current. So what we can do, we can use a higher DCR inductor that will have a smaller size. Lesser the DCR, bigger the inductor is, because it requires thicker coil. So low power inductors will be smaller in size compared to high power inductors. So now we require, so still you can reduce the size of the inductor. Maybe after packaging it may not scale by 2x, but still maybe 50% reduction you can, not 50%, 20-30% reduction you can still see by using a lower power inductors here. So if this is R loss and this is also R loss, this is going to I load by 2, I load by 2. So total loss, assuming same power stage as, assuming each phase has the same. So first I will do with, like, let's say I just copy the same converter multiple times, which means I am increasing the size of power FET, like 2 phase 2x, assuming each phase power stage same as single phase. That's why I kept it R loss, not twice of R loss. If you shrink the size by 50%, that it will become 2 R loss. So what is the total power conduction loss? I square R. So I load square by 4 in 1 into R loss multiplied by 2. So half of which is 50% less. So if you keep the same size, then in multi-phase your conduction losses will be lesser, because each phase is carrying only half the current. Now assume total size of power FETs is kept same as single phase, then this will become twice of R loss. Now do the same thing. So you will get I load square by 4 into twice of R loss into 2, which is same as single phase. So ultimately you may not benefit in terms of losses, but still the benefit is in the ripple. So you can achieve the same ripple with the smaller cap. Okay, but now let's say same thing I want to do for the boost. You know, current is boosted there. So your inductor current is I load over 1 minus D. Let's say I am operating at 50% duty cycle. So 1 amp current, load current, inductor will be seeing 2 amp current. Now split in the two, each will be seeing only 1 amp current, correct, because 500 milliamp, the 2 amp will be split into 2, because each will be carrying 5 equivalent to 500 milliamp load. So there you may say more benefit compared to buck in terms of losses, and losses will cause heat, and sometimes you may require heat sink. So the size of the heat sinks depends upon how much loss is in your converter. So you can reduce the size of your heat sink in a multi-phase compared to a single phase converter. And same thing you can do if you are using same inductor and same power stage, obviously here, but at the extra cost. So that's the only difference. Issues with multi-phase converter. There is one very common issue. Can anybody think of that? So all the assumptions are that both are carrying the same current, both phase. But who will decide they are carrying the same current or not? How will you ensure that they are carrying the same current?
Same equivalent resistance.
Capacitor will not decide. Capacitor is carrying only ripple current.
With same RDCR. Same RDCR is there.
But we cannot ensure that. Let's say 20% mismatch. But why will that be a problem? I fail to understand. Let's say one DCR is higher, other is lower. So if the current is not equally split, then why is that a problem? If R loss is more, I want to reduce the current. So automatically that will do that. So it's an advantage actually. If there is a R DCR mismatch, then the current which in the inductor which has a lesser R DCR will be more, and other case it will be higher. If you assume the duty cycles are same, correct? Because average voltage across the inductors, both inductors are same, but resistors are different. So the one which has a higher resistance will carry a lesser current. So that is benefit for me, because now it's a well balanced actually. Otherwise that R is higher, I square R losses will increase there. So that's not a problem actually. That will in fact help in your efficiency, in a way, average efficiency. The problem is if a duty cycle is mismatched, what will happen?
Inconsistency.
So one will have a higher current, other will have a smaller current. I mean your loop will try to regulate the loop. Even if duty cycle mismatch, your loop will force in such a way that your average duty cycle will look like same. Okay. So that's not a problem actually. Regulation is not a problem. The problem will be current balancing. So the current balancing is the main issue here. Mismatch duty cycles of causes So think about this. Let's say this duty cycle mismatch in such a way that instead of carrying 500 milliamp each, one goes 600 milliamp, other goes 400 milliamp. That may happen, So the one which is carrying 600 milliamp will see a higher loss, other will see a smaller loss. On an average, quite possible that average loss may be higher compared to if they are equally split. Okay. So, that is why we require current balancing here, which means you have to ensure that, and we know that it is because of the duty cycle mismatch, you have to match the duty cycle. So, we are using a single control voltage. So, who will cause the mismatch here? Ramp will cause the mismatch, or comparator offset, or let us say delays in the comparator, that will also cause mismatch. And ramp, obviously, I mean, we are charging a capacitor with a current, and those two currents may have a mismatch. So, and that is why we require a current balancing. So, in the current balancing, what you do actually, you take this control voltage. So, instead of connecting like common, each one will have, so let us say if this is IL2, IL1,
Instead of adder, let me add some additional control. Sense 2.
okay. Same thing you do on the other side. So, what you take the V control and you take the sense current from both actually. So, I sense. So, what is the current required at each phase? I sense 2 divided by 2 equal to I average. So, you compare each current with I average and see if it's higher or lower, and then based on that you decide whether duty cycle needs to be increased or decreased. So, same thing is required. We don't have a space here, but same thing is required on the other side also, because you don't know which one needs to be increased or decreased. Okay. So, basically you have to do in one side you have to increase, other side. So, let us say 600 400 milliamp instead of 500. So, the 600 milliamp has to be 500 milliamp, so which means reduce it by 100 milliamp, and the other side has to be increased by 100 milliamp. So, you compare with the average whatever the required, and we are already, so this requires your current sensing, and we know how to do the current sensing. So, it requires extra hardware, extra complexity, all those there in multi-phase. So, this is the main problem actually with the multi-phase. Yeah, it will do. So, in this case, it will always, it doesn't care about why it is. So, but when it balances with a different RDCR, the impact in efficiency is very small compared to if this mismatch is due to the duty cycle. And you can do that calculation, because that mismatch, I mean, that RDCR is already very small. So, that mismatch will hardly impact 1 or 2% mismatch or even 10% mismatch. You will see efficiency impact won't be that much. But if you create a 1% difference in the duty cycle, that efficiency impact will be huge actually. So that's why you don't care about, even if it reduces your efficiency due to mismatch in inductor little bit, you don't care because that impact is not as high as mismatch in duty cycle. But if you have a weight where you can determine whether this mismatch is due to RDCR or due to duty cycle, then and that is also quite possible. You can both measure both the duty cycle at the switch node. So this you can always measure the duty cycle at these two, VSW1 here and here. Ultimately, you are interested in the end duty cycle. Huh?
Instead of having this sense current, can we have like the information of duty cycle only controlling?
Yes, you can do that. Most of the time, we do like. If you can measure your duty cycle in a very high resolution manner, I mean, 0.1% or so, you can do that. But in the time waste, we don't get that problem actually, because you tap the phases and they are already all phases are matched. I mean, the delays will cause a mismatch. So, I mean, let's say I have 5 delay cells in the ring. I have 5 delay cells. So it's a 5 phase. I can tap 5 phases from there, but ensuring the each delay cell is exactly same or matched, it's very difficult. So the phase to phase mismatch may be there. That may cause difference in the duty cycle, multi-phase. So in that case, what we do, instead of running the VCO, let's say I want 10 megahertz, I will run my VCO at 50 megahertz and then divide it by 5. So it's, again I will get a 10 megahertz, but since they are divided, overclock and then divide, so all the phases will be matched, perfectly matched. So you won't have any mismatch problem there. And that's what we did here actually, if you see. This guy. So here actually, it's 1 to 4 phase we are tapping, and this whole VCO is running at, if it's a 70 megahertz and 17 to 4, 280 megahertz actually. That's what it is running at, this VCO. And then here it's nothing but, you can think of multi-phase generator is nothing but dividing this clock by 4 and separating out all the 4 phases. So single phase goes here at 4x and then separated out in 4 phases, rather than tapping the 4 phases directly from the VCO, because that may have mismatch. So here you get a very good phase match. But the VCO is running at 4x, so it will have some extra current obviously. But if you compare this extra current by running the VCO at 4x and what complexity and the current you require to generate for the current balancing and all those, that is much simpler here. Because current sense itself is not a simple okay. So each compared with ILS and okay. So you can subtract, add depending upon if you know how much it is required, or it may have its own integrator also, because you are comparing something, it will generate an error. That error can be accumulated and that code digitally you can correct the duty cycle, or you can implement in an analog way and add or subtract the voltage from V control, which is going to the comparator. So now this will be VCTRL dash, I will call it. It's a new control. Okay.